If you've ever worked on a complex embedded system, you know the feeling, right? Your code starts out simple, a nice clean loop. But before you know it, it's this tangled mess of flags, interrupts, and weird timing bugs. It's just chaos. But what if there was a better way? A way to bring real order and control to all that complexity? Well, that's exactly what a real-time operating system, or RTOS, is for. Today, we're going to break down the best practices to get you from that bare metal chaos to the structured, powerful world of an RTOS. So here's the plan. We'll kick things off with why you'd even want to make this leap. Then we'll dive into the absolute essentials: how to manage your tasks, how to optimize for memory and speed, picking the right synchronization tools, and you know it, what to do when things go wrong and how to debug like a pro. All right, so let's get right into the why. For so many of us, the embedded journey starts with what we call the super loop. You know, one giant, endless loop that just checks everything and does everything. And look, it works for simple stuff, but as your system gets more complex, that whole approach it starts to fall apart. And RTOS offers a totally different and frankly, a much better way to structure your code. And this right here just says it all. On the left, that's the super loop world. The code gets brittle, you change one little thing over here, and something totally unrelated breaks over there. It's a nightmare to maintain. But on the right, that's the RTOS approach. Your application is split into these small, independent tasks. The whole thing becomes organized, way easier to maintain, and way more responsive. It's a total game changer. Okay, so you're sold. You're using an RTOS. Great. Now, we need to talk about the absolute heart of your application. The tasks. Think of them as tiny, focused mini-programs. Getting this part right from the get-go is, and I mean this, it's absolutely non-negotiable if you want a stable system. So, here are 4 golden rules you just gotta live by. Rule number 1, statically allocate your tasks. Don't create them on the fly. Doing that can lead to all sorts of unpredictable memory problems. 2, avoid changing task priorities while the system is running. Seriously, it's just a recipe for bugs that you will pull your hair out trying to find. 3, use time slicing. This makes sure that if you have a few tasks at the same priority level, they all get a fair shot at running. And finally, this one is huge. Watch your stack usage. Things like recursive functions or really big local variables can cause a stack overflow, and poof, your whole system crashes. All right, let's tackle the biggest myth about using an RTOS, the #1 fear that holds developers back. They think it's going to be this massive memory hog that slows the whole system down. They're worried about the overhead. But is that really true? Let's find out. And this quote, this just hits the nail on the head. It is the #1 objection, the main reason people stick with that chaotic super loop we talked about. But let's look at the actual numbers, the real data. So here it is. This is the reality of that so-called overhead. A modern, well-designed RTOS kernel, it typically only uses about 2 to 4% of your CPU. That's it. I mean, for the incredible benefits you get in organization and stability, that is a tiny, tiny price to pay. So yeah, myth busted. And you can absolutely keep that footprint small. Here's your checklist. First, plan your architecture before you start coding. Think about what you actually need. Second, analyze your stack usage so you don't waste a bunch of RAM. And finally, if you do need dynamic memory, use deterministic memory pools. They give you fixed-size chunks of memory and prevent the kind of fragmentation that can kill your system's performance. So, once you have all these tasks running, they're eventually going to need to talk to each other or share something. Now, an RTOS gives you a whole toolbox for this, but using the wrong tool, oh man, it can be a disaster. It's like trying to use a hammer to turn a screw. It might kind of work, but you're going to make a huge mess. This table right here, this is your cheat sheet. Let's walk through it real quick. Let's say you need to protect a shared resource, maybe a communications port. You look under mutual exclusion and boom, a mutex is the preferred tool. What if you just need to signal that something happened? Like, hey, new data is ready. For event notification, a semaphore is your go-to. And for actually sending data between tasks, look at inter-thread communication. The message queue is the clear winner. The big takeaway is to always match the problem to the preferred tool. It'll save you from so many headaches. Now, the most common mix-up by far is between semaphores and mutexes. They are not the same thing. A semaphore is basically just a signal. It's fast, it's simple, it's great for event notification. A mutex, on the other hand, is all about ownership. Only the task that locks a mutex can be the one to unlock it. And critically, a mutex supports priority inheritance, which is a fancy way of saying it prevents a high-priority task from getting stuck waiting on a low-priority one. They are built for different jobs. Look, even if you follow all the best practices, bugs are going to happen. It's just a fact of life. But debugging in an RTOS world introduces some new and tricky challenges. Problems can seem random because they depend on the exact timing and interaction between all your tasks. So you need a smarter toolkit to hunt them down. Here are some of the classic RTOS villains and how to defeat them. Priority inversion, we just talked about that. A mutex with priority inheritance is designed specifically to fix it. Deadlock, where two tasks are stuck waiting for each other forever, the fix is discipline. Make sure all your tasks lock resources in the exact same order. Thread starvation, where a task never seems to get a chance to run, that's a design problem you solve upfront. And stack overflows? Here's a great pro tip. Fill a task stack with a known pattern, like all A's, when it starts. Later, you can check to see how many of those A's have been overwritten. That's your high watermark, and it tells you if you're getting dangerously close to the edge. So let's put together your essential debugging toolkit. First, use assertions liberally to check your assumptions. Second, use a trace tool. This is like an EKG for your software, giving you a visual timeline of exactly what's running and when. It's invaluable. Third, enable that stack monitoring we just talked about. And finally, learn to read your CPU's fault registers. When your system crashes hard, those registers often hold the only clues as to what went wrong. So I'll just leave you with this one question to think about. Our embedded systems are only getting more and more complex. That's a given. The real choice we have as developers is this. Is our software architecture going to manage that complexity and keep our system robust? Or is it going to become part of the problem, making our code more fragile with every new feature we add? Using an RTOS with the right practices, well, that makes all the difference.